Today we begin our lecture 12. It's in focus. So we begin with lecture 12. Let us recall the things that we did last time. We talked about the concept of a vector space. Then we talked about the concept of a subspace. So just as a reminder, vector space was basically a non-empty set which had two operations, one about addition, one about multiplication by a scalar. And we said it is closed under addition and multiplication by scalar, and it had total 10 axioms that we talked about. Various laws like distributive law, commutative law, existence of zero, existence of inverses. So all those things we had talked about. And subspace was basically a subset of a vector space. Which is a vector space in its own right. So this is like so-called, I would say, crude way of putting things, but since it's a reminder, so I'm just giving the essence of it. So subspace of a vector space is a non-empty subset of a vector space, which is a vector space in its own right. And we had seen how to check something is a vector space, how to check something is a subspace. So let me recall, for subspace, all we needed to ensure was that if I say a subset S of my vector space, V is a subspace, then it should be non-empty. And it should be closed under addition. And the third thing we want is it should be closed under multiplication by scalar. Now these two things can be combined under one simple idea, and we can say that S is closed under linear combinations. Okay. So if we pick two vectors in here and form every possible linear combination, all the combinations thus formed would be inside set S. So what this means, so what I'll do is I'll try to give you the meaning of it. So if I pick two vectors, let us say u and v, which belong to my set S, and suppose C1 and C2 are real numbers. In general, you can call them as the scalars, depending on the field we are using. But since our attention most of the time will be real numbers, so then this is a subspace if we can guarantee that C1U plus C2V will always be inside S. So if it is closed under linear combinations, then we can say that our set S is a subspace of our vector space. Okay, so this is what I'm just trying to recall in a nutshell of things that we saw. Now what we'll do is I'll come up with some examples of how addition and multiplication can be defined on different sets, something which is less familiar to us, and we'll check whether they will form a vector space or not. So let me construct some simple examples first that can help us understand or sort of come out of our comfort zone. So here is one example. So here is my space, here is my set. This must be a very familiar set to us. Basically, I am saying let us again look at the two-dimensional vectors in real space. However, this time I'm going to define my addition and subtraction slightly differently. So this time I'm going to say that suppose you want to add two vectors x, y, and say a, b. This is how you're going to add. So x plus a, y plus b. So this is my definition of addition, which is the same as what we have seen so many times. Here is my definition of multiplication by a scalar. Notice that I want to define it like this. I'm only multiplying the second component, not the first one. Okay. Suppose this is my new definition of addition and multiplication by a scalar. The question we are asking is V a vector space? Under these operations. Okay. So what it means to say is that we are taking a familiar set, namely R2, but this time we are trying to come up with a different way of adding things and multiplying scalars, so that in some sense it will lead us to a different kind of geometry. Now under this new set of operations, will it still be a vector space, or will one of the axioms or some of the axioms go wrong? So what we'll do is we'll go through all the axioms one by one and see if all of them are followed, or is there a problem somewhere. So let's try to analyze, is this a vector space? So first of all, we'll talk about closure. So let's talk about the closure part. Is closure under addition there or not? As you can see, it is the usual addition, the way we add things. So if I pick a vector in V, I pick another vector in V. As you can see, the only criteria for something being in V is that both of these are real numbers. So I would say closure under addition, it is the usual addition. Hence, I am guaranteed the closure. Okay, so that is something which is which we can check fairly easily. Now we have to worry about closure under multiplication. Is it closed under multiplication? Well, let's see. If I pick a vector in R2 in V and multiply it by a scalar under this definition, the first component and the second component both belong to R. So suppose I pick xy in V, and suppose I have a scalar C, then C times xy, which is basically xcy, both the components, so both x and cy are in R. This implies this vector xcy will also belong to V. Hence it is closed under multiplication also. So closure is not a problem. It is closed under both these operations, so maybe it is a vector space. But remember, we have to talk about other axioms. So what I'll do is I'll pick one or two axioms as an example just to illustrate the process. And then we'll see if we are able to randomly come up with an idea of which axiom may fail in this case. So let's try the axiom about the zero vector. Is there a zero vector? Well, I claim that 0, 0, which is a member of V, is the zero vector. Now, the easiest way to check is, let us perform the addition defined on V. Based on the definition of addition, we are going to get this. So existence of zero vector is guaranteed to us, and hence at least this axiom about existence of a zero vector or an additive identity is also taken care of. Okay, so we have a zero vector. What about commutativity? Is the addition commutative? That means if I switch the order of these guys, will I still get the same vector as produced before? Instead of checking all these axioms one by one, let us apply some common sense. This addition that we have obtained, we have defined for V is the same as we had already encountered in R2. So any axiom which is only based on the addition of vectors will still be true in V because we are just using the same old definition of addition. So if at all things are going to go bad for us, it should be somewhere where multiplication is involved, because scalar multiplication is defined in an unusual way. So if at all there is a problem, it should be there. So I'll pick one axiom from about multiplication and try to check it whether it holds or not. So let me try to pick this axiom about remember we had one of the axioms about the distributive law that C plus D times U must be C times U plus D times U, where C and D are scalars. Question is, will this be true here also? So what we do is, we'll make a check. We'll do a check and see if it is worth it or not. So first, let us have our vector U, and let us have our two scalars. So C plus D times U will be C plus D times the vector xy, and the vector x, and based on the multiplication we have been given, this would be x times C plus dy. Based on the addition we know, I can split it as x cy, x, sorry, let's not split it at this moment. Let me just go a bit slowly. Suppose I come to this point, x c plus dy. Question is, this is my left hand side, will it equal the right hand side? So let's try to understand what the right hand side will look like. So cu plus d, this would be c times xy plus d times xy. Based on our multiplication, this would be x cy plus x dy. Now the question is this quantity that we have obtained here, is this right hand side equal to the left hand side? Now if you add the way we have defined addition, this would give you 2x c plus d y. Okay. Now if you look at this, definitely these two things need not be equal for all values of x. So that means this axiom will fail in this particular given set. Hence, so what we have obtained is that c plus d times u need not be the same as cu plus du. Hence, it is not a vector space. So what it means is that I try to define a new operation on an old beast, and this failed to be a vector space. What does this mean? Does this mean that this R2 can only be a vector space in the usual way of adding things and multiplying things? Because it seems to be failing in the new way of defining things. Or does it mean that only this is an operation for which we couldn't have a vector space structure, but there might still be an operation on the same set where things will turn out to be vector space, and it will be different from our usual way of looking at R2. So we can look into that. But the main emphasis of this problem was to show you that you have to go through all the axioms. I was lucky enough to hit in the first time which axiom is going wrong. Partly based on experience, partly luck. But in a sense, you can go through all the 10 axioms, and if even one of them fails, then you are guaranteed it's not a vector space. Let me show you something slightly different and see if things will turn out to be nice. Okay. So here is a new set, and I'll try to define new operations on it. So here's my new set V, which is basically all real numbers which are greater than or equal to 0. Or let me actually take out 0 because I don't want to create a problem. 0. So all positive real numbers. You can think of it as all positive real numbers. Now, I give you a definition to add things. Here is how we will add. So x, we will add it to y, will be as x times y, and c times x. Now here is something that you should be very, very careful about. C is a scalar and x is an object in this set. And this is how we are going to define x raised to the c. So c has to be from the set of real numbers. Remember, it has to be a field. So c could be any real number, positive, negative, 0, anything. So these are the two operations we have defined. Okay. Question is V a vector space under these operations? So is V a vector space under V vector space? Okay. So let me, just for the sake of illustration, let me just highlight it so that we keep on looking at it and remind ourselves that we are dealing with some new operations. Okay. So what I'll do is I'll first go through closure and then we'll talk about some of the axioms. Okay. So here's my closure under addition. suppose I pick two objects, x and y, belonging to V. So the criteria for them to be in V is that both are positive real numbers. Then x plus y, we are defining it as x times y, which is the usual multiplication. And for sure, if x is positive, y is positive, therefore x times y would be positive. So this implies that x plus y will live inside, hence closed under this addition. Okay. Now we try to go for closure under multiplication and see if that also works there. So this is closure under scalar multiplication. The reason I'm using these special symbols is just to illustrate that we have defined some special operations. So here we pick a scalar, it could be any real number, and we pick x to be an object from our set. Then c times x, we are defining it as x to the c, and since x is positive, this implies x raised to the c will also be positive irrespective of what c is. Even if c is negative, it will be just 1 over x to the c, which is a positive number. So this implies that this object is still inside V, hence closed. So it is closed under both addition as well as multiplication. This weird way of defining things, but nevertheless, as you can check, we have shown without any ambiguity that these operations do hold. Now what I'll do is I'll pick two more axioms and I'll leave the rest to you for exercise just to see whether those axioms will hold or not. So I'll just pick at random an axiom that we can check. For example, let's talk about the zero element. What would be a zero element in this case? Now remember, zero element, let me give it some name. Let me call it as Z. Zero element. So what should be the property of the zero element? Zero element when added to any other element should produce me the same element. Okay. So for any x, for all x in V, if I can find such a Z in V which can do this for me, then it'd be nice. So what is exactly that we want? We want x plus z should be equal to x, but the way we have defined x plus z, which is x times z, should be equal to x for all x. This means x times z minus 1 should be 0 for all x in V. Now this can only happen if I take z to be 1. Since 1 is positive, so we can guarantee that z belongs to V. It's a positive real number, and I claim that 1 will act as the zero element. This also should kind of serve as an indicator that we should not think zero element being as the zero number always. Zero element is an element which is going to act as additive identity. So you should not be led by the phrase zero element, it's just for convenience. What you should be thinking about is an object which is going to act like zero acts in regular addition. Okay, so as you can see, we have found in a so-called zero element, z is equal to 1 is our zero element. So let me note it down somewhere. In fact, until we have the zero element, we couldn't even have talked about the inverses or additive inverses. But now that we have the zero element, we can definitely talk about additive inverse. So why don't I show you additive inverse also as one of the axioms. It will help us understand this process a bit better. So now that we have our zero element, let's see what would be an additive inverse. So inverse of an element. Okay. So suppose X is in V. Then we are looking for an element. Let me call it Y. Y is fine. Now I'm using Y over there, so let me use something else. We want some T inside V such that X plus T would give me the same thing as T plus X, and that would give me the so-called zero vector. Remember, Z is our zero vector. Okay. So in essence, let me just check one of them. X plus T, we want X plus T to be Z, which means we want XT to be equal to 1. So this means I want my T to be 1 over X. So 1 over X would be, if it exists inside V, then this can act as an inverse of our element. Now 1 over X is going to be positive because we know that X is a positive real number. So this means this guy definitely belongs to V. So for each X in V, we have found its additive inverse as 1 over X. So let me note down this fact also. These are some special things that will help you think outside the box a little bit. So for each X in V, 1 over X belongs to V will be its additive inverse. Okay. So as you can see, based on the existence of the zero element, we were able to find the additive inverse. And actually this should bring this actually brings out a point. Since I want T to be 1 over X, definitely I cannot have X to be equal to 0, and that is why I had removed 0 from there, because I wanted every element to have an additive inverse. So that is why 0 had to be thrown out. So we have shown the existence of zero element, existence of an inverse. So in some sense we have shown about what? 1, 2, 3, 4 of the axioms being true out of the 10 possible. So I'm not going to go through all 10, but I'll check one more, which involves scalar multiplication. And we'll try to check whether it holds or not. If it does, then it can further ensure that we are kind of coming close to proving it to be a vector space. Again, I'm not saying it is a vector space, but if one more axiom holds, then we are pretty much in that territory. Okay, so let's see. Which axiom do we want to check? Okay, let's check the same axiom which kind of gave us the idea last time. So this axiom, C plus D times U, is C times U plus D times U. I've deliberately written it in that form so that we keep reminding ourselves the kind of operations we are using. Okay, so C and D are real numbers, and for our vector u we take x, which belongs to v. So keep in mind x is positive. Okay. So we'll go with the left hand side. So we go with the left hand side, which is c plus d times u. For us, this would be c plus d, which is a scalar, times x. And by our definition, this would be x to the c plus d, which we know using the rules of exponents is x to the c times x to the d. Now we can say x to the c is nothing but c times x, and x to the d is nothing but d times x. But this is a regular multiplication, so this can be now interpreted as addition in our case, and hence we have c times x plus d times x, which is the same as saying c times the vector u added to d times the vector u under that addition, and this happens to be your right hand side. So this happens to be your right hand side, hence we have shown that that axiom also holds true with these particular operations on this particular set. So it appears that there would be really something special if this does not turn out to be a vector space, because the intuition says even if such a law can hold true, then the chances of any other law getting derailed are less. But that doesn't mean it could still have a problem somewhere. So it's up to you to check whether it's a vector space or not. In fact, if you look at these operations, you might get reminded of something. If you look at this, addition is acting like multiplication, and multiplication is acting like exponentiation. So it should remind you of things like logarithms and exponential functions. So the idea of this comes from there. If I have to give you the answer, then I would say it will turn out to be a vector space under these operations. You can check and verify that all the axioms will hold true. So moral of the story is, when we say something is a vector space, we have to also pay attention to the operations. And it could happen that the same set is a vector space under different types of operations. So never think that R2 is a vector space only under the operations that we are used to. In fact, R2, we can have other kinds of addition and multiplication under which it will still be a vector space. So this brings us to an important question, not the one which we can perhaps answer here, but something to think about. If I give you a set and I define two sets of addition and multiplication, and somehow it turns out to be a vector space under both those operations, will the two vector spaces be the same, in the sense isomorphic, or will they turn out to be different? So this is something to think about. We don't want to make it abstract over here. It's just curiosity. So my question, I'll just phrase it. Suppose I have a set V and I define an operation of addition and multiplication. With the same set V, I define another operation of addition and multiplication. And it turns out to be vector space under both these operations. Will this be isomorphic to that or not? It's a kind of a deep question. which you may not be able to answer now with the amount of exposure you have, but something worthwhile to think about. Okay. Let's come to further understanding the subspace structure. Let me get this out of the way. So let's come back to things. I had made a comment in the previous lecture that all the subspaces of R2 are, so one was R2 itself, the other was just having the zero vector, and the third thing was all straight lines through the origin. I had made a kind of a statement which I never proved. I said these are the only subspaces of R2 and there is no other. Question is, why are these the only subspaces? So this is the question which we want to possibly answer now and see if we are in the position to answer it. Now, you will have to recall, I had already shown you that the set containing just the zero vector is always a subspace. Of course, the entire space has to be a subspace by default. And I had also shown you that all straight lines, I had proven that all straight lines that pass through the origin will be a subspace. So that is not in jeopardy that these three things are subspaces. Question is, why are these the only subspaces? So I'll try to give you an idea of the proof. The proof is not very involved, but here is a basic idea that can help us. Now, suppose I have a subspace of R2. If S has only the zero vector, then nothing to prove. Because we have already shown that the set containing just the zero vector is always a subspace. So now assume that S has some non-zero vector. So let U belong to S such that U is not the zero vector. So that means S has a non-zero vector. Now since S is a subspace, this implies that it must be closed under multiplication. So that means C times U must belong to S for all scalars. What does this mean? This means, from the geometry point of view, if I have given you that my subspace contains a non-zero vector, let us say that non-zero vector is U. By the closure property, it will contain every multiple of U. So it will contain all multiples of U. So that means it contains a straight line that passes through the origin. Okay. contains the straight line that passes through 0, 0. Now, if S does not have any other vector, that means this is the totality of vectors. So, if S has no other vector, then S is basically a straight line through origin, and hence a subspace. So that we already know the straight lines through origin are subspace. So now the real question is, if S had only the 0 vector, it was the 0 space. If S had a non-zero vector, then the entire straight line will sit inside. And if S has no other vector, then it is a straight line. But what if S has another vector which does not lie on this? So now the question is, what if there exists a vector V in S such that V is not on the line that passes through the origin and is in the direction of the vector U. That means V lies outside. What happens then? So I'll give you an intuitive idea first and then we'll go about. Suppose I find that, I have a vector V, which is, let us say, somewhere here. This is my vector V, which does not lie on this line U. Then what could possibly happen? Remember, S is a subspace. So if S is a subspace, it will have all possible linear combinations of U and V. So imagine what will happen if I have all possible combinations of U and V. This will give me the entire space R2. So that means if S is not the 0 space, it's not the straight line through the origin, then S has to be R2. Then the span of the vectors U and V would be R2. This is the only thing where you have to fill in the details. Why should the linear combination of U and V give me everything? In fact, I'll give you some hints for that also, so that you know how to fill in this gap. So let me give you a simple way of thinking about it, and perhaps that can fill in all the gap I'm looking for. So here is the idea behind it. We are saying that you give me U and you give me V, which does not lie on the same line as U. Then U and V can linearly combine to produce any vector I want. So that means you give me any vector in R2. And I will be able to find some linear combination such that U and V can combine to produce me W. Now remember, this is a column picture. So what we are saying is that if I have the coefficient matrix with U and V as my column vectors, then no matter what right hand side I give you, this system would be consistent. Now, since U, since V is not a multiple of U, what does this mean? This means the set of vectors U and V is linearly independent. So this is linearly independent. This means what? If I call this coefficient matrix as A, so the coefficient matrix A is invertible. And from the fundamental theorem of invertible matrices, columns of A will span so the columns of the coefficient matrix A will give you every right hand side. Or you can think in this way, since these are independent, I will have two pivots. Since we are living in a two-dimensional space, no matter what right hand side I give, this system is consistent, and hence it has a solution for every right hand side. Which means what? Which means the moment I have a vector which lies outside this line, these two vectors can combine to give me tan R2. That means the only subspaces of R2 can be only the zero space, the line passing through the origin, or R2.